Hello friends, last class I discussed about the basic gates of the digital electronics, right? And respective truth table also I discussed. Okay, and where we can use the such kind of the basic gates application in the practical life. This also we discussed. Okay, so today we'll discuss about the what is the Boolean expression and what are the properties of Boolean expression and some universal gates. Okay. So Boolean expression here I told Boolean expression means suppose for a AND gate. Suppose for a AND gate, Y is the output and A and B, these are the inputs, right? So this is called the Boolean expression. What are the expression you are representing in digital electronics? These are called the Boolean expression. Boolean expression means the expression which consists of two numbers, two kinds of the variables. One is the 0, another is the 1. Okay. So that's why it is a Boolean expression. Okay. Now there are the different Boolean expression, and suppose you have the multiple inputs, 4 inputs, 3 inputs, right? In a system you have the multiple inputs, 2 inputs, 3 inputs, like that. So you will get an expression, okay, which contains multiple product terms, okay, multiple some adding summation terms you will get, right? So for reducing some expression you need some properties. So if we proceed with the circuit, if you want to deal with the complex digital system, so we have to handle, we will handle with we have to dealing with the different kind of the circuits, okay, or different kind of the logical expression. So sometimes we have to minimize those kind of the logical expression, right? For that we need some properties, okay. Suppose based on the true and false, based on the truth, all are related to basic gates only: logical multiplication, logical addition, and the complement of the input. Okay, three basic gates are there: AND gate, OR gate, and NOT gate. Okay, so based on three gates, you have lots of properties. Okay, right. So first basic properties are like that. Suppose you have one input, if we add same input with that the same, if we add this one with the same input, you will get the this one. That means a logical operation between a plus a is equal to a. That is the logical operation between similar input, that will get only the same input, right? So if we add 1 plus a, you will get 1. So whatever value, either a value of a is 0 or 1. If you add any input with the 1, you will get the 1. Okay. So another thing is that a dot a, that is also is equal to a. If you multiply a with the a, you will get a, right? So more apart from this, so double complement. Okay, double complement of this is equal to 1. If you complement a, again if you complement the complement of a, that you will get the same input variable. Okay, right? So 0 plus a, here you will get a only. Okay, if you add 0, this is normal, like a normal addition also, you get it. So 0 dot a, that is equal to 0. Now if you are dealing with the same, only single input, right? So if you are dealing with the two inputs but both inputs are same, right, or single input, a plus a, 1 plus a, 1, a dot a, right, a complement of double complement of same input is same value. 0 plus a is equal to a, 0 dot a is equal to, how we are getting, suppose a 1 plus 1. So if suppose your value is 1, a is 1, 1 plus 1, 1 in logical operation, I know. If a is 0, 0 plus 0, it is 0. If it is 0, 1 plus 0, 1. That we know from the OR gate, logical addition. 1 plus 1 is also 1. In this way you can write. So here it is, suppose your value a is equal to 0. So if you invert a, you will get a 1. Again, if you invert this one, you will get 0. 0 means a. Okay, from where you can get these properties, right? So apart from this, now I am coming to the two inputs. Okay, two different kind of the inputs. Okay, suppose a plus b is equal to b plus a. Okay, so So, so I am reducing this one. What I will check what we will get. Okay. So, this is one kind of property suppose. So A dot A. A dot A means A. Right. A dot B. So I can again take in common A. Sorry. This is 1 plus B. So one property is that 1 plus B. That is also equal to 1. So here it is 1. So this term is reduced to A. This is a one kind of the property. A within bracket A plus B. You have the two inputs and the two inputs like this is one kind of the logical expression. You have such kind of the logical expression. Instead of writing this expression, you can directly write this as A. Right? This is a one property. Okay. Another property suppose A prime B. Okay. So here it is. A prime, A, B. Okay. So this property is there. So A dot A prime. This is will be 0. Okay. A plus A prime. This I forgot to tell. That is equal to 1. Okay. So A dot. If you multiply same number with the complement of the same number, you will get 0. And A plus, if you add same number with the complement of same number, you will get 1. Suppose A is 1. Suppose A is 1, right? So here I am writing 1 dot complement of 1 is 0. So that is 1 dot 0 is 0. Okay. Again, if you write A as a 1 in this equation, 1 complement of 1 is 0. 1 plus 1 is 1. Suppose if A is equal to 0, if you put this formula, 0 dot 1 is equal to 0. Again here if you put 0 plus 1 is equal to 1, right? So here it is 0. Here it is A, B, right? So you are getting A, B. So if this expression is there, you can write A, B. If this expression is there, you can write A. Okay, this you can reduce, right? So next another one property that is dealing with, if you deal with the three inputs. So we have one expression. This is A plus B into A plus C. Okay. So I am trying to reduce it. So A dot A plus A dot C plus B dot A dot B, both are same, right? B dot C. Okay. So here you will get A, from A dot A you will get A, right? Rest terms remain same. So from this term I am taking A, that will be 1 plus C. Again A plus BC. 1 plus C, that is equal to 1, that I told just now, right? So A plus AB plus BC. Okay, again if you take an A common, 1 plus B plus BC. So this is equal to A, 1 only. A plus BC. So now here you can see. So if you have A plus B into M plus C, you can write A plus BC, or you have such term. Okay, A plus BC, right? So you can write as A plus B into A plus C. Okay, got it? Right? Clear? So this about the some properties I discussed. First I told if you have single input, some properties are there. If you have two inputs, some properties are there. This is the, if you have the three inputs, some properties are there. Okay. So you have to remember those properties, right? So if you remember those property, you can minimize some kind of the expression. Suppose you see now. So you have, if you have the A plus B into B plus C. Okay, it can be reduced to A plus BC. Okay, so this is how, if you are dealing with the complex system, complex digital system, you have to give the multiple inputs and you will get the output corresponding to logical function. So in output you will get the large expression. So by using those properties you can minimize those large expressions, right? Okay, so these are the properties. Now come to the apart from this property, so two more properties are there. This is called De Morgan's properties. Okay, there are two properties. First property I am writing, suppose 1 plus b whole prime. This means if you add two inputs, 1 plus b, and if you do the complement, here you will get the a dot b dot. That means addition of two inputs, complement of addition of two inputs, that is equal to, if you complement two individual input, after that if you multiply those two inputs, you will get the same results, right? So I'm verifying it. Okay, suppose here a b, here will be a plus b, a plus b prime, a b, and a dot b prime prime. Okay, okay, here I am writing a prime b prime. Okay, this I verify. So this should be equal to this. This I verify. The truth table same value will get in these two column. I am verifying. Okay. Suppose for how many combinations are there? Two inputs are there. So 0, 0, 0, 1, 1, 0, 1. If two inputs are there, you can write four combinations, right? So for that, so for corresponding this, here it will be 1, 1. A prime will be 1, 1, 0, 0. Here will be 1, 0, 1, 0. Okay, I am just doing this one. A plus b. A plus b, you know, 0, 1, 1, 1. That means from this truth table. This truth table, okay. 0, 0, 0, 1, 1, 0, 1. If any input is 1, output will be 1 for logical addition. Okay. So now complement of a plus b. This I am doing complement. Whatever result you are getting, I am doing complement of this result. That means inverse I will get. If 0 is there, here you will get 1. Here you will get 0, 0, 0. Okay. Now, okay. So here I am doing a dot b. This is not required. This is not required. Okay. So now you can see a prime b prime. I have to do this thing. Okay. So a prime dot b prime 1 dot 1. You know, if you multiply 1 with the 1, logical multiply 1. 1 with the 0, 0. Again 0 with 1, 0. 0, 0, 0. Okay. So now you can check these two tables. These both values are same. Corresponding these two columns, these both values are same. Right? So you can write as a plus b complement is equal to a prime dot b prime. This is the De Morgan's one theorem. So if you want to draw the logical diagram, okay. So in this case, first you have to do the addition, okay. So I am taking a and b. I am doing the addition, logical addition, okay. Here I will get a plus b. So you have to complement. So that means I have to put a not gate for complementing, okay. This you can write like this way. This is equivalent to, right? Now I am drawing the logical expression, logical diagram for this expression. So complement of individual input, and then we have to do the logical multiplication. So I am first complementing a. Here it will be a plus a. Now I am complementing b. I have to check first complement, then multiplication. Here first addition, then complement. Okay, first addition, then complement. Here first complement, then multiplication. Okay. So here you will get a prime, here you will get b prime. Okay. Now I am multiplying. Okay, here you will get a dot b dot. So these two circuits both are equivalent. Okay. So this is the about. So here first I have to complement the individual inputs. I am complementing individual inputs by using two NOT gates, and these two inputs are entering into the AND gate for getting a prime dot b prime. Okay. So this is the logical multiplication of complement of individual inputs. That is equal to complement of logical addition of two inputs. Okay. Second De Morgan's theorem. Second De Morgan's theorem. Second is the, okay, here is the complement of logical multiplication, that is equal to logical addition of the complement of two inputs. Both are different. Okay. So first one was like that. Complement of logical addition, that is equal to logical multiplication of individual complements. Okay. Here it is complement of logical multiplication, that is equal to logical addition of complement of individual inputs. Okay, these two are the De Morgan's theorem. So again I am verifying these equations. So here I am writing A, B, okay, A dot B, A dot B prime, A prime, B prime, A prime plus B prime. Okay, so I am verifying this thing. So here 0, 0, 0, 1, 1, 0, 1, 1. So A dot B, you know, logical multiplication. If both inputs are 1, you will get 1, otherwise you will get 0. Complement of this result. Okay. So if you do the complement of this result, in these three cases you will get 1, here you will get 0. Now I am complementing A. Okay. So 0, 0, 1, 1, it will become 1, 1, 0, 0. Again I am complementing B. So 0, 1, 0, 1, it will become 1, 0, 1, 0. Now I am doing the logical addition between these two inputs, right? So 1 plus 1, 1. 1 plus 0, 1. 0 plus 1, 1. 0, 0, 0. Now you can see this column and this column both are same. So that is validated, right? So this I can write as a this is equal to this. Okay. Now you want to draw the logical circuit diagram. I am drawing here. Okay. So here first we have to do logical multiplication, then complement. So I am doing the logical multiplication for getting A dot B. Now I am complementing. I am putting NOT gate A dot B complement. That is equivalent to. So here first I have to complement to both inputs. Then I have to do the logical addition. Okay. A prime, B prime. Then I am adding both the inputs. Okay, so these two are the same. Okay, these two diagrams are same. Okay, now so basic gates. So I told about NAND gate or NOT gate also. Okay, and XOR gate. So basic gates are NOT gate, basic gates. Basic gates are NOT gate, that is complement, AND gate, logical multiplication, OR gate, logical addition. Okay, so universal gate. These are the NAND gate I told, and NOR gate. NAND gate means if you add AND gate and NOT gate, you will get NAND gate. NOR means if you add OR gate and NOT gate, you will get NOR gate. Okay, another gate is that is the XOR gate. Okay, so this is the different from these two gates. So you can design XOR gate, these three gates, and this gate by using these two universal gate. So if you want to know the truth table, okay, for getting the truth table of NOT gate, AND gate, OR gate and XOR gate, you can use the only NOR gate and NAND gate. Without using the AND gate, OR gate, NOT gate and the XOR gate, if you want to need truth table for OR gate, AND gate, NAND gate, AND gate and the XOR gate, so by using the NAND and NOR, you can design those gates. Okay. So first I will tell NOT. Okay, NOT gate using NAND and NOR. Okay, so how we will get NOT gate? This is the symbol of NAND gate I told, and then the on top. Okay, so here we will get NOR gate by using the NOR gate again. So this is, so here it is A. Here we will get A prime. It should get A prime. Okay, so what I am getting for NAND gate? So the same input we are entering as a two inputs of the NOT gate. Okay, NAND gate. Okay, that means what is the formula for NAND gate? A two inputs, complement of two inputs, right? A dot A complement. Okay, so here we will get A dot A means A. So A prime. Okay, that means this is my input, this is my output. This is output for NOT gate. Okay. Now again, here I am writing. So what will be the output for NOT gate normally? So you have the A but two inputs. You are connecting A in two inputs, right? So two inputs are A only. So what is the logical complement of OR gate? Okay. So A plus A complement. So A plus A, you know A, that is A. So from here you are getting A complement. So these two gates are equivalent to NOT gate. So if you to short both input terminals for NAND gate or for NOT gate, NOT gate, you will get the NOT gate. Okay. Now AND gate. Okay. AND gate using NAND and NOT. Okay. So one AND gate I am placing a separate two inputs I am giving. For AND gate you should have the two inputs, right? So again the output of the first NAND gate that will be entered to the input of the second NOT gate, but the same output should be connected with the both inputs of the second NAND gate. Okay, you should get A dot B. I am just checking. Okay, so this is NOT gate, NAND gate. Here I will get A dot B complement. Okay, now think. So what you will get here? Again, this is entering as a, so A dot B. Okay, this is one. This is the input for this NAND gates, right? But here two inputs are there. So that means logical multiplication of two inputs then complement for NAND gate. If you remember A dot B complement, that means so complement of logical multiplication. Complement of logical multiplication. Okay, so from De Morgan's theorem, you can write as A complement plus AB complement. Okay, so from from De Morgan's theorem, I can reduce these to these. Okay, so complement of logical expression, that is individual complement, logical addition of the individual complement. So this prime will cancel because I told that A is equal to A prime prime. Okay, here you will get AB, here also you will get AB. So AB same input. If same two inputs are there, then you will get the same thing AB. So I am getting AB. Okay, so for if you want to use the NOR gate, how we will use? You have to do like this way. Here we will get AB. Okay, right? I'm just checking. Here, if this is NOT gate, right? You can see this is NOT gate. So that means this will be A prime, this will be B prime. Okay. Now here we will get input, then this one. Okay. Logical complement of logical addition. Here I am giving A prime and B prime as a inputs for this NOT gate. Right. If you use the De Morgan's theorem, that will become this thing. Okay. So here you will get A dot B. This complement will cancel out. Right. Next is the OR gate using NAND and NOT. That is reverse of the AND gate. Okay. So for OR gate, I am just writing. If you want to do using NAND gate, here you will get. Okay. So suppose here it is A, here it is B. This is NOT gate, as I told. If you want to design, if you want to implement NOT using NAND, this will be the NOT gate. Okay. Here you will get A prime, here you will get B prime. Now this is the logical in giving A prime and B prime as inputs and then complement. That is the NAND gate, output of the NAND gate. Okay. If I use De Morgan theorem, it will be like this. A prime prime, that is again A plus B. So I am getting the OR operation by implementing this circuit. Okay. Now for NOT gate, if you want to use NOT gate, it will be like this. Okay. So A and B you are giving here, for output of the NOT gate will be A plus B complement, right? So this is again NOT gate. That means again NOT gate. That means you have to complement this input. This should be the input, right? So complement of this thing. Complement of this thing. Again you will get A plus B. So either you by using this one you will get logical addition, or by using this one you will get the logical additions. Okay. So by using the De Morgan's theorem you can prove that. So this circuit is equivalent to and this circuit is equivalent to or, and this circuit also equivalent to or. Okay. So you can use either NAND or NOT for implementing the OR gate, or again you can use NAND and NOT for implementing AND gate also. And XOR gate also you can implement by using the NAND gate and NOR gate. Okay, this we will check later. Okay, so this is about the all the basic gates, Boolean expression and properties, and how can you design the basic gates by using the universal gates. Okay, so next class I discuss about the SOP, POS, and this thing will the sum of products. How can you represent logical expression in different terms? This I will discuss on next class. So please subscribe my channel and like and share. Thank you.